Most of us have been exposed to lasers in some form or another, whether it was your standard red laser pointer, often used during lectures or to harass your cat, in DVD and CD-ROM drives, playing laser tag as a kid, barcode scanners at the grocery store or library desk, or even one of the more high-powered green laser pointers, often used to point out stars in the night sky. Lasers are all around us. They have become so commonplace that we hardly even notice. You have also probably seen advertisements for laser eye correction as well as laser hair removal, both of which use much more powerful lasers than you would normally be exposed to day to day. Although lasers have become incredibly common, I bet you probably know very little about how they actually work. To start, did you know that laser is actually an acronym for light amplification by stimulated emission of radiation? There are a number of different types of lasers, and in this video we will go over the basic physics behind just one of these, and then move on and explore two of the laws that govern how the light emitted from a laser acts, the law of reflection and the law of refraction. The two most common types of lasers are gas and solid-state lasers. In this section, we will cover how a solid-state laser works. On the most basic level, a laser is able to emit light by adding energy to a mass of atoms, which causes them to emit photons. Once one atom randomly emits a photon, this rogue photon further stimulates the atoms around it and causes even more photons to be released. If this was all that was done, there would be light emitted, however not in a concentrated beam that you would recognize as a laser. In order to get the beam even more powerful, the mass of stimulated atoms is placed between two mirrors, which traps the photons and causes them to bounce between the two mirrors and through the mass of atoms over and over again. This causes the atoms to become even more stimulated and thus release more photons. All that is then needed is a small hole in either one of the mirrors, which releases a concentrated stream of photons which forms the laser beam. In a solid-state laser, the mass of atoms is a solid, most often a crystal. The first working laser was created using a ruby as the mass of atoms. In this video of a gas laser, or heme laser, spelled H-E-N-E, after helium neon, the parts can clearly be seen. On the ends, there are two mirrors, which focus a beam of light through the helium and neon gas center. This is the red glow that you see. If the mirrors were lined up perfectly, there would be a laser beam emitted from the exterior.
This beam of light can be directed to follow a predictable path. In this image, the ray of light approaching the mirror is known as the incident ray. The ray of light that leaves the mirror is known as the reflected ray. At the point of incidence where the ray strikes the surface, a line can be drawn perpendicular to the surface of the mirror. This line is known as the normal line. The normal line divides the angle between the incident ray and the reflected ray into two equal parts. The angle between the incident ray and the normal line is known as the angle of incidence. The angle between the reflected ray and the normal line is known as the angle of reflection. Three things can be concluded based on this law. Number one, the incident ray, the reflected ray, and the normal line to the reflection surface at the point of the incidence lie in the same plane. Number two, the angle which the incident ray makes with the normal line is equal to the angle which the reflected ray makes to the normal. Number three, the reflected ray and the incident ray are on opposite sides of the normal line. These three rules give us the formula theta 1 equals theta 2. To show this formula, we'll use a laser reflected off a mirror and measure the angle against a protractor. As we can see from this picture, the angle of the reflected ray and the incidence ray make the same angle to the normal line. Both degrees are 40. This follows our formula theta 1 equals theta 2. Most of us are pretty familiar with the concept of reflection, but did you know that light also refracts? Refraction can be seen in rainbows, prisms, mirages, and even light patterns on the bottom of a swimming pool. Lasers will also refract when hitting surfaces such as water or glass. Here's a diagram to help us understand the law of refraction, or Snell's law. The idea of the incident ray and the normal line are the same as the law of reflection. However, The refracted ray bends off towards the object, creating an angle from the incident ray to the normal line. This is angle theta 2 in the diagram. This angle will change depending on the refractive index of the surface. Greater refractive surfaces create smaller angles to the normal line. This law gives us the formula n1 sine theta 1 equals n2 sine theta 2, where n1 and n2 are the refractive indices of the medium, and the two thetas represent the angles between the two rays and the normal line. We will use these ideas and test them with plexiglass and a laser. Here we see the angle that the laser creates with the normal line is not equal to the angle that the refracted light makes with the normal line, but instead follows our formula n1 sine theta 1 equals n2 sine theta 2. Because light behaves in predictable ways, we can easily apply laws of reflection and refraction to predict incident and reflective or refractive angles. The two formulas, theta 1 equals theta 2 for reflection, and n1 sine theta 1 equals n2 sine theta 2 for refraction, show us that the angle of incidence and the angle of reflectivity. These laws can be used to find the reflective and refractive surfaces of the eye in customizing contact lenses, and have many other purposes as well. In lasers specifically, the mirrors and laser cavity allow for a highly concentrated light to follow a straight line, which allows for the laws of reflection and refraction to be possible.